So the first thing we're taking a look at is what would the graph of this function look like? So it's a square root function. I can see that. It looks like it's been moved right 2 and up 3. So I put my first point there, and then I make my normal square root graph from there. Now once I've made that graph, now I want to see what would the graph of the inverse look like. Now you've got a couple options for graphing an inverse. One is you find the equation, the inverse equation of the original. But I don't want to do that in this case. The other option is you take each of the original points, you take their coordinates, and you swap the x and y coordinates. So, for instance, my first point, remember, was at 2, 3, because I went right 2 and up 3. If I swap those, 2, 3 becomes 3, 2. So that means my inverse is going to include the point 3, 2, which is going to be right over here. I repeat that for each of those points. So for instance, the next point that I see plotted there is at 3, 4. And so my inverse point is going to be at 4, 3. And if you have trouble doing it visually, write the points out like that. It's a great way to keep track of it. And then the last point that I clearly have plotted there at least is at 6, 5. And so, of course, that's going to become 5, 6, right? Because inverse means swap the x and y coordinate. Once we've plotted each of those points, then we can go ahead and sketch the graph that goes through it. All right, so now that we can see our original function and its inverse graph, take a moment. What would the domain and range be for each of those graphs? Go ahead and think each of them through, please. All right, so for those domains and ranges here, I'm going to start with my original, so that's the one in blue there. My first thing is domain, which is my x value. You can see I start at x at 2, so I know it's going to be x and it's going to be 2, and my x's are getting bigger from there because I'm going to the right, so it's x is greater than or equal to 2 for my original domain. Now for range, I'm dealing with the y value. So it starts at a y value of 3, and it's going up from there. So my y's start at 3, and if they're going up, that is greater than or equal to 3. Now I could get the inverse by going over and looking at my graph the same way, but I'm not going to, because that requires just 10% more thought than my other method, which is just to switch the domain and range of my original to get the domain and range of the inverse. So my inverse domain is going to be greater than or equal to 3. The only difference is that instead of y is greater than or equal to 3, it's going to be x is greater than or equal to 3, because of course domain is still describing my x values. Same thing for my range. My range comes from my original domain. Everything about it is the same except that the x becomes a y. And so there I have my inverse domain and range. Now, notice none of them are all real numbers. That is critical here. Because what if we go and we find the inverse equation of our original function here? Well, if I'm going to go ahead and find the inverse equation, that means starting by swapping x and y. Of course, remember, g of x, that's just a fancy name for y. So if I swap x and y at the start, I end up with x equals the square root of y minus 2 plus 3. Okay, subtract 3 from both sides. That gives me x minus 3 equals that same square root. Now that I have the square root by itself, I square both sides. That's going to give me x minus 3 squared equals y minus 2. You don't need to worry about squaring it out here. You can go ahead and just leave it like this, x minus 3 squared. If you want to expand it, it's not wrong, it's just unnecessary. Last thing you do, add the 2 to both sides. And so we end up with a final answer then of x minus 3 squared plus 2. Now you can write it as equals y, or you can write it as y equals, either way. But in the end, since I started with g of x, I'm going to call that inverse of g of x. But there's our equation that we just found. But think about this. This equation here does not give this graph. If I were going straight from just that equation, I actually would have a graph that has both sides to it. I'd be looking at something more like that. But then my inverse graph doesn't look the same as my original. Well, if I were only graphing this, my domain would be all real numbers. But notice, the actual inverse does not have a domain of all real numbers. That's why we found that domain earlier. Up until this point, domain has always been a way of describing a graph, and that's the way I've always talked about it with you, as a descriptor of the graph. But it actually isn't just a descriptor. A domain can actually do work for us. We can use domain to actually restrict a graph. Because really what I want to say is that this is the inverse, except it's only this half of it. It's only the stuff to the right of 3. And so I add a little bit to my answer. I say this is the inverse provided that x is greater than or equal to 3. Now notice, that statement right there, x is greater than or equal to 3, that's the exact same thing as our domain of our inverse that we found earlier. And so how do we know what it is? Well, we found our original range, so original range. Then we swapped that to become our inverse domain. And that tells us what that restriction is. Now for today's work, this is actually the first half of what we're learning new today. The other half deals with compounding interest. And so for that half, we're going to take a look at this problem to start with. So suppose you put $500 in a savings account which pays 0.25% annual interest. And yes, this is fairly reasonable number. Some of you are thinking, wow, isn't 0.25% pretty low? No, actually, that's a pretty good rate nowadays. Nowadays, an average savings account gets you more like 0.01% interest. But we're going to work with a nice optimistic number for today's work. How much will be in the account after 8 years? And we're going to write the equation that models the situation and use it to answer the question. Now, if I were trying to do this without some fancy equation, I'd have to do a lot of work, because I would have to do 500, and I'd have to figure out what is 0.25% of that. Well, to figure out what 0.25% of something is, I first turn that 0.25% into a decimal, which is 0.0025. And so I multiply that by 0.0025, and that tells me how much interest I earned after 1 year. But then I'd still have to do the original plus that amount. So really, in order to be able to figure this stuff out, we have to take our original plus the original times 0.0025. I don't want to have to do that every time, though. That's a bit of a pain. So instead, what we can do is we can actually make a little tweak here. Since I'm trying to include the original amount, I could actually multiply it by 1.0025. Because that way you're representing the original whole. So we started with $500, and then we added that 0.0025. So the additional interest we earn, we write it in decimal form, but we add it to 1. And that'll give you the new amount every single year. Well, if I want to do this for 8 years, I would have to do that times 1.0025 times 1.0025 to figure out how much we have after the second year, times 1.0025 to figure out how much we have after the third year. We got to do this 8 times. Do you want to actually have to write that out 8 times and press equals on your calculator 8 times? Certainly not. There's a shorter way, right? What's a shorter way to represent multiplying something by itself 8 times? Exponent. Yep, exponent. So instead it could look more like 500 times 1.0025 to the power of 8. And that's how we can put it together. Now this is a very quick and dirty version of what that would look like. Some of you prefer to have a nice equation that you can plug the stuff into. We will be coming back to this problem in a moment. But you might want to add this into your notes first, and then we'll go back to that problem. All right, so taking a look at this, let's just take a look at some little details, make sure you understand all the ideas about what all's going on here. First of all, when you see a parentheses t equals, remember that is function notation. That's not a times t, that's a of t. So it's basically the value of a when t equals whatever the value is. Now notice that I use the phrase time periods. The most common way that this formula gets used is when time periods is actually specifically years. So like if t was measured in years, then this would be the number of years here, and this would be the number of years here, and it would tell us the amount after that many years. But we leave it ambiguous as time periods because technically you could also use the same thing if interest is compounding monthly or daily or all sorts of other little creative things that you might want to throw in there. And then remember when you deal with the R, please make sure that you remember from the start that we always have to write our percent as a decimal. If you're a little rusty on that, you either move the decimal 2 places over or divide it by 100. Whichever way you remember it, of course, it means the same thing. And in case you're wondering why did I use principal here, because you'll notice this is a formula that comes up in lots of other places. It's always written as P, and I just want you to know why it's called P. Plus, it's also good to know that principal is just a fancy term, especially used in finance, meaning what you started with. All right, so now that I have this, I can go back to that problem that we started with and see how we can apply it to this situation. So we're being asked in this situation to figure out what there will be after 8 years. In other words, I'm trying to figure out what A is going to equal. So A is what I'm trying to find out. A is my answer. What is the value of P going to be here?
$500.
Yep, that is the 500. Because P is our starting amount. Our principal means starting amount. So P is going to be 500. Then I need a little r. R here. Remember I take my percent and I turn it into a decimal. We talked a little bit about that earlier with this one. So it's going to be 0.0025. And again, you could get that answer 2 different ways. You could move the decimal over twice, or you could take the 0.25 and divide it by 100. If you're rusty on that, I hope you've written that down, as I've said it twice now, about how you turn the percent into a decimal. All right. And then the last thing we got to put in is the value of t. In this case, t is going to be the amount after 8 years, so t is 8. From there, it's just a matter of plugging all that stuff in. And so our equation looks like this when we just plug into the formula. 500 times 1.0025, all to the power of 8. And so once you have the equation written, it's an order of operations problem. Now you notice there's a few different things going on here. We got multiplication going on between the 500 and the parentheses. We have addition taking place within the parentheses, and we have an exponent. What do I do first?
Parentheses.
Yep, stuff inside the parentheses. PEMDAS is hopefully what you're thinking about there. So we do the stuff inside the parentheses first. Once we've done that, do we do the multiplication or the exponent next?
Exponent.
Exponent, exactly. PEMDAS, P first, that was parentheses, then E, the exponent's next. So I do the 1.0025 to the power of 8. And then multiply that by 500 to get your final answer here, which is about $510.09. Now you'll notice I did not specify what to round to here. Would I expect you to round to the hundredth place like this? Yes. This problem is dealing with money. Anytime you're dealing with money in a problem, I'm going to assume that you should know round it to the nearest cent. That is, round to the nearest hundredth, always. Now, the opposite can happen as well. Things don't always grow by the same percent each year. Sometimes they can decrease by a certain percent each year. Well, we want to be able to do the same basic process here. We want to show what happens if the amount is going down by 0.25%. So this was the equation that we had earlier. What about it am I going to change to make it go down instead of make it go up? Yeah, our addition here is actually going to become subtraction. The reason is because basically what's happened is that R is no longer 0.25%. it's like R is now a negative 0.25%. And so when we add a negative, of course, that becomes subtraction. So whenever you're decreasing by that amount, you subtract instead of adding. All right, now when we do this work, of course, we do the stuff inside the parentheses. Then we're going to raise that number to the power of 8 and multiply it by 100 if you've done that correctly. You should get an answer here of $490.09. Now, it's always great to be looking for patterns in math, and some of you who are really attuned to looking for patterns might be looking at this and thinking, oh, our original one ended in 9 cents when we were going up by that amount. This one also ends in 9 cents. Is that always going to happen? No. That just happened to be the case here. So there's no like consistent rule of symmetry or something that you'll be able to follow in that regard.